How's it going, everyone? We're going to be talking about uranium enrichment, and hopefully after this video you'll have a much better understanding of conversations that you hear going on about nuclear energy, nuclear weapons, and uranium enrichment in that context. We'll talk about uranium itself, what's the whole point of enrichment, and how enrichment is achieved. So, in the top corner here, you have a photo of uranium in its raw form. Underneath that, you have a photo of processed uranium. And uranium can be found usually in two different forms. There's uranium-238 and uranium-235. And understanding the difference between these two is very important in understanding enrichment. And to discuss that difference, we have to get a bit into some particle physics. So, all matter is made up of atoms, and in the center of those atoms is the nucleus, which contains protons and neutrons. The protons are positively charged, the neutrons are neutral. The number of protons in an atom's nucleus determines what element it is. For example, uranium has 92 protons in its nucleus. If it didn't have 92 protons, it would not be uranium. It is uranium specifically because it has 92 protons. But the numbers here, 238 or 235, represent the number of protons plus the number of neutrons in the nucleus. And these are called different isotopes of uranium. So uranium-238 has 3 more neutrons in its nucleus than uranium-235. Okay? And when uranium is found in its natural form, about 99.3% of it is uranium-238 and only about 0.7% of it is uranium-235. But uranium-235 is the one that is needed for production of nuclear energy or for nuclear weapons. And the reason why is right here. See, uranium-235 can take part in a process of fission, which means it can be broken apart into two smaller elements. If a neutron hits uranium-235, then that neutron can actually break apart the uranium-235 atom. For example, the diagram here shows it breaking up into krypton and barium. So specifically, you have a neutron, which is a little blue dot on top, hitting the uranium-235 atom just below it. Periodically, we have uranium-236, right, because a neutron has been added to it, and that number represents the total number of neutrons plus the number of protons. But then that uranium-236 breaks up into krypton-92 and barium-141. Now, if you add 92 and 141, you are 3 short of 236, right? You only get 233. So where did those 3 subatomic particles go? Well, these are the 3 neutrons that you see flying away at the bottom of the screen, right? So we started with 1 neutron hitting a uranium atom, and we ended up with the uranium atom split and 3 other neutrons flying away. Now those 3 neutrons might go on to hit other uranium-235 atoms, and those uranium-235 atoms might break up and release more neutrons that might hit more uranium-235 atoms, and the process continues as such, and this is called a nuclear chain reaction. And each time a uranium atom is split, energy, heat, is released, and that heat could be used to generate nuclear energy if it's a controlled nuclear chain reaction, or it might generate a nuclear explosion, which is a nuclear weapon. Now, in order for this chain reaction to occur, there has to be enough uranium-235. And what we see in uranium's natural state, only 0.7% of uranium is uranium-235. Well, that's not enough. You need 3% approximately, maybe a bit more, for generating nuclear energy in a large number of nuclear power plants. There is a nuclear power plant design, the CANDU design, which actually doesn't need uranium enriched. But for many, many nuclear power plant designs, you need uranium enriched so that 3%, maybe a bit more, 3, 4, 5% of the uranium is uranium-235. And for nuclear weapons, you need it enriched to about 90%. Okay, so 90% of your uranium is uranium-235. So the question is, well, how do you do that? How do you increase the concentration of uranium-235 when in its natural state only 0.7% of uranium is uranium-235? And so there's different ways to do this, but a very, very common way is using a phenomena that actually has a lot to do with the kind of thrill ride you see in front of you. Okay? It has to do with phenomena called the centrifugal force. Now, it's not actually a force, it's a fictitious force, but that's what the phenomena is called. And what this is if something is spinning around some axis, then it tends to move farther away from that axis. For example, in this ride here, where you have this spinning disk connected to swings, as the disk starts spinning, the swings actually tilt away from the axis of rotation. Now, you may have experienced this if you're driving in a car, and let's say the car turns towards the left, you feel yourself moving away from the point that the car is rotating around as it turns, right? And you might experience this as a sensation of being pushed to the right as the car is turning left, or pushed to the left as the car is turning right. Or maybe if you've danced with someone while locking elbows and you're kind of spinning around each other, you might feel a sensation of you're being pulled away from that other person, okay? So here's what that phenomena is. So if you have some point of some point around which there is rotation, and let's say there's a mass which is rotating around that point. Well, this mass is moving forward, right, in a direction that is perpendicular to the path from the axis of rotation to the mass. It's like if you're on a carousel, you're always moving forward, whereas the axis of rotation is to your side. But the rotation itself curves your trajectory towards that that axis of rotation, and so you end up rotating. Okay? Now, here's the thing. If you're moving sufficiently fast, or if you are sufficiently massive, well, then it can be difficult to change that forward velocity. And so although your trajectory will still curve towards the axis of rotation, it'll still be somewhat stretched away from that axis, right? So you are still rotating, but you're farther away from that axis, okay? So now in this picture here, your velocity is still forward from your perspective, but it's still being curved towards that center. Instead of remaining on a circular path, you move even further away, and so on. And that's why when something is rotating, the more massive it is, the more it tends to move away from that axis of rotation. Now, when we're talking about uranium-238 versus uranium-235, uranium-238 is heavier because of those extra 3 neutrons. So here we have a diagram of a centrifuge. And we're looking at it from the side, so it's actually spinning like this, okay? And what you see here as it spins is that the uranium-238 moves farther away from this axis of rotation, right? See, it's moving farther away because it's heavier. And as it's moving farther away, it's displacing the uranium-235, so the uranium-235 ends up moving closer towards that axis of rotation. Now, you could also set up rotation which is vertical, like this, for example, by heating the bottom, right, which will cause the hotter uranium to move up. By the way, this is uranium in gas form, so we're talking about a fluid. Specifically, it's uranium hexafluoride that's being pumped in here. So you have the heavier uranium-238 moving towards the outside and downward and into these outlets here, right, and out of the top here. and you have uranium-235, which is lighter, moving closer towards the center and up and through these outlets here. And so you're separating the more enriched uranium, which has a higher concentration of 235, and the more depleted uranium, which has a lower concentration of uranium-235. And that enriched uranium, you can later enrich it even more in this kind of centrifuge again. And you can just keep repeating that process and get uranium to be as enriched as you want, right? So your uranium-235 concentration is 3% or 5% or 90% or whatever one needs. And on the diagram, this might look pretty straightforward, but it's actually a pretty difficult technology to develop and use. And so not everybody has this technology, and it is a separate technology from mining uranium or from producing nuclear energy, right? So uranium might be mined in one place, it might be sent to another country to be enriched, and then from there the enriched uranium might be sent to another country to be processed into fuel and then used for nuclear energy. And here is a photograph of actual centrifuges. They are quite tall, right? We're talking meters in height, not feet, okay? So these aren't like big spinning buckets, okay? These are like very large, tall cylinders. So I hope that clears things up and helps you understand the discussions around nuclear energy, nuclear weapons, uranium enrichment, and until next time, enjoy.